Hi, in this video, I create the temporary stand-in for the memory module. It goes quick, so I end up spending a little bit of time talking about the requirements for the fetch module related to the different addressing modes we're going to have for the instructions that the computer will support. Let's get right into it. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. In this video, I've got the breadboards back out, and I want to start working on the stand-in for the memory module. And so I've got my clock here, it's running, and I've got it on the automated mode. Recall I can put it into single step mode and push the button there. And you can see here, I've got the clock and inverted clock. I want to bring in my register, which again is breadboard at this point, and plug it in so that I can get my clock hooked up to it and some control lines hooked up to it. And I've got 3 places I plug into this distribution point just to make sure that I've got enough power being distributed throughout the entire breadboard. I don't want to run into any power problems. And then if you'll recall, when I was testing the register PCB, I put this quick control circuit together, and I want to get it plugged in as well. And a couple of things here. I have this clock that I'm going to pull from the clock module, and then what it's going to do down here is this is a pull-up resistor, but the clock is going to override that, and it's also jumped over here to this, where I have the increment set. So rather than push the button here to cause an increment, the clock is going to cause an increment and latch, such that when I plug this in to the register, the clock should start counting. Now, my inputs right now are all floating, and what I did is I brought this little blue breadboard in so that I could bring everything to a single location. And when I plug that in, I have some basic counting going on. Now it started off with some unknown value there, so I'm going to clear that. And I am asserting onto address bus A, which is what this line is, and I've just overridden the button so I don't have to keep asserting that. So asserting out onto address bus A is my fetch clock, or my fetch bus. So I'm going to plug this in and take these 2 up here and plug them into what would be address bus A assert, or address bus A. And you can see that I now have outputs here onto address bus A. And the goal today is to take that address bus A information and plug it into what will be my address bus module here. I can give it power and ground. And I'm just taking them from here just as a random spot. And then ultimately the goal then is to take the output, so this would be output from this would be output from the memory module, which would then go on to address the fetch bus. So address select, let me get the proper hookups here. Well, I didn't think this through well. Let's see here. So there's my address bus coming in for the fetch cycle. My outputs would come off that into what would be ultimately my fetch register. Now, initially my thought was to just have these tied with pull-down resistors. And that would in effect give me a no-op into the fetch register. And I thought, well, there's nothing really to see with that. I can't prove to myself that it's actually working the way I want it to. So what if I was just to pick up what was being fed into the address bus 1 as its output, and then treat every single possible instruction as a no-op in order to get things debugged? Well, this then now becomes, this section right now, as it stands right now, becomes my stand-in for the memory module. And that feels like cheating a lot. And I'll buy that. It probably is. But what it does is it gives me the ability to build the fetch module, the fetch register and the instruction register, and have some valid data being passed on through. Now at this point it makes sense to talk a little bit about the addressing modes that we're going to have with the assembly language instructions, what I intend to support. Whether everything comes to pass or not, I'm not absolutely certain, but I think we're going to be able to get very close on most of these things. So the first thing I want to call to your attention is that there could be, well, there are 11 different addressing modes that I'm going to support, and there's no significance here in the number other than the fact that I just started at 0 and started numbering them. There are instructions that are going to take no arguments associated with it. A halt instruction might be an example of that, or a break instruction, each of which are not going to carry, the arguments are implied in the instruction. Another one of those might be clear carry or set carry, clear overflow, set overflow. Those would all be things where the argument associated with the instruction is built in or baked into the instruction itself, therefore it's implied. So there's no addressing mode. There could be an immediate, such as a jump to a specific address. The constants I intend to start with a prefix with a $sign, whereas an immediate indirect is an address where the left and right square brackets are, you can think of them as defining a cell of memory. And so 1, 2, 3, 4 then becomes the address of that cell of memory, and we're going to jump to the contents of that cell. So the address would then be held in memory address 1, 2, 3, 4. I'm going to skip a couple of these because I'm really, in this case, concerned with the constants. So I could load a register with an immediate value. Again, this is just a constant value, 1, 2, 3, 4. I can load I could store a register out to a memory address, and 1, 2, 3, 4 then becomes the memory address. And then, of course, we're going to reference the cell therein. So you use that as the store instruction. Load instruction is very similar. And then these, again, don't have constants associated with them. So it's these 3 addressing modes and these 2 addressing modes that I want to be very concerned with. And what I have done is I've gone out and defined, if you will, what clock cycles would look like for my fetch register and then my instruction register. So if I was to move an immediate value into register 1, the fetch register would then have that, fetch that instruction and pass that on to the instruction register in the next clock cycle. And also the fetch register would then have the constant. It would be part of the data stream that comes into that fetch register. So ultimately what I need to be able to do is I need to be able to assert this onto the main bus, the 1, 2, 3, 4 constant value. Put that onto the main bus such that it can be latched into register R1. But the other requirement is that the fetch register has to then pass on a no-op to the instruction register. And they're all very similar to this. For example, if I want to add a value to R1, I end up with that constant in the fetch register, and then I want to be able to assert that onto ALUB because it becomes a second half of that argument into the ALU. And then again, it has to pass the no-op onto the instruction register. If we're going to do a jump instruction, so we're going to jump to a new address, say that we're going to jump to address 0 and start the program over again. Again, we need to be able to assert this onto the main bus. The program counter would then latch that new address. And again, the fetch register is required to pass a no-op onto the instruction register. And then the last case, store and loads are very similar in that you end up with an address that ends up in the fetch register, and that needs to assert onto address bus 2 for the instruction register to operate on. And then R1 then is what gets asserted onto the main bus, but the address 9ABC gets asserted onto address bus 2. And then, of course, the fetch register is required to pass a no-op on. We don't want this 9ABC or the zeros or any of these constants to turn into instructions that then get executed. So that said, that then gives me a list of where I need to be able to assert my data from the fetch register. I need to be able to pass that on to the instruction register, or alternatively, pass on a no-op instruction if that information in the fetch register is a constant that needs to be passed on somewhere else. Somewhere else could be the main bus, it could be ALUB, it could be address bus 2. There's no reason to put it into address bus 1 because that's what's actually fetching the instructions into the fetch register. There's no reason to pass it on to ALUA because that is always the left-hand side. ALUA is the left-hand side of any binary operation. The right-hand side would always end up being a constant. And then the main bus, there's no reason to swap the constants. You should have done that when you wrote your code. So there's no reason to have an instruction to swap a constant that's coming off the instruction string. So those are my 4 interface points. And with that, then I can start plugging components into the breadboard. And I'm not going to do that today. In the next video, we'll start putting together the fetch register, which honestly is just a watered down version of this. So I lose 2 of my asserts. I don't need to assert onto address bus 1. I don't need to assert onto ALUA. I'll lose 3 of my asserts. I don't need to assert onto the swapped main. So I only have 3 asserts there. I add an assert for, I'm pointing at address bus 1, but it's really to pass up to the instruction register. And then I need to be able to pull that down if nothing is being asserted. So we have to have a little bit of extra logic specifically for that. I don't need the counters, but I do need the latch chips. I do need to be able to display the output and contents of that. And then of course I want to have some LEDs to indicate control. So it's going to end up being probably 4 breadboards for the fetch register. And I'll start dropping components into breadboards in the next video. Thank you. We'll see you soon.